you about carbocation rearrangement. So last time we talked about doing carbocation rearrangement in a predict the products kind of sense, where if you have a carbocation intermediate and it's a secondary carbocation adjacent to a tertiary or quaternary carbon, you can predict that a 1,2 hydride or a 1,2 methyl shift, respectively, will lead to a more stable carbocation. We talked about drawing both the rearranged and the not rearranged products. And I told you it gets more complicated than that, and just wanted to show you one example of that. So this molecule, are you scared yet, is a precursor to cholesterol. This is called linosterol. It's actually 19 more steps before you get to cholesterol. But this is a precursor to many hormones and vitamins. Vitamin D is made through the same pathway. As I said, cholesterol, progesterone, testosterone, estrogen, cortisol, cortisone, all of these come from this same basic core structure. We'll actually talk probably later in the class how you get all of this from a precursor that's just a line of carbons. But I wanted to show you a series of carbocation rearrangements that occur. Earlier on in the synthesis of this molecule, you end up with this carbocation with a positive charge on this tertiary carbon. And what happens then to get from here to here is a series of rearrangements. You can sort of see that the carbon in my starting material here that's positively charged ends up with a hydrogen on it. And then I have a double bond here in between two carbons where there's in the starting material both a hydrogen and a methyl group. So a lot has to go on to get from this starting material to here. And you end up with this cascade of reactions. One of these is a 1,2 hydride shift. So you have an empty p orbital on this carbon and a CH bond that can align with it. And so that hydrogen leans over with its electrons and makes a new bond with the carbon that was originally involved in the carbocation. And so there you go. In so doing, the old positively charged carbon gets the CH bond, the new positively charged carbon is there. There was a question last time about stereochemistry and whether it matters, and indeed it does. The proton that shifts over was down, and it is still down after the shift, and so that stereochemistry can be communicated through the process. Before you start panicking, realize I wouldn't ask you to predict that this would happen, but if you know what the starting material is and you know what the product after the rearrangement is, you can pretty well figure out that it's this one arrow that makes this happen. We're not done yet because we're not to the final product. There's a series of other shifts that occur. Oh, and before we move on, I'll point out that this carbocation shift takes you from a tertiary carbocation to another similar in energy tertiary carbocation. Now remember, I told you that I'm not only going to have you predict that a carbocation rearrangement will occur when you have a secondary carbocation adjacent to a tertiary or quaternary carbon, because that's a situation where the rearrangement gives you a more stable carbocation. So I'm just telling you that I wouldn't have asked you to predict that this would happen, but if I told you that it did, could you draw the arrow that would explain it? There's a series of other 1,2 shifts here. This hydrogen, which is down, shifts over to the adjacent carbon, so the carbocation is now here. Then this methyl group, which is up, does a 1,2 methyl shift to make this carbocation, and then this methyl group, which is down, does a 1,2 shift to make this carbocation, and then the final step is an E1-like elimination step where a base from the enzyme that catalyzes this process removes, oops, we didn't want to erase, just point, removes the proton, creates a double bond, and there's your linosterol. So there's this cascade of 1,2 hydride and methyl shifts that gets everything where they need to be. Okay, so you'll see that again in biochemistry, but now you'll sort of know what happens. Very few people actually draw all these intermediates. Instead, they'll draw the 1,2 methyl and hydride shifts all sort of in the same step. There's some evidence that might be true, but the story's more complicated than we need to get into. Anyway, example of carbocation rearrangement. By the way, your body's been making cholesterol all the while we've been sitting here talking about it. And it's been much faster at it than we can talk through this. Okay, so our theme today is how do you avoid carbocation rearrangements in substitution reactions with alcohol. So far our theme has been use acid to turn the OH into a good leaving group. So today we're going to talk about some alternatives to that. And again, I'll just warn you, there are going to be details here that make sense. There's also going to be nuances that are complicated and for which we don't really have good explanations. I'll try to be pretty clear about what you're going to just need to memorize and what you can understand based on mechanism. All right, so alternatives to adding acid. We want to avoid the carbocation intermediate. All right, option 1 is a reagent called PBr3, which we're going to use instead of HBr to turn the OH into a good leaving group and to replace it with bromine. All right, so I'll show you just sort of a standard reaction. We'll talk briefly about mechanism. The reagent is phosphorus tribromide, or PBr3. The effect of this reagent is to replace the OH with bromo, but the mechanism of that replacement or substitution is SN2 because you see this enantiomer only. And I want you in your mind to contrast this with what we did last time, which was if you take this chiral enantiopure alcohol and use HBr, the mechanism is going to be SN1 such that you get both configurations of the stereocenter. Okay, so this is synthetically useful in the sense that you can avoid starting with a chiral starting material and getting racemic products. If you use PBr3, you only get the desired enantiomer. Okay? If you were going to flashcard this reaction, remember you'd make your 3 flashcards where basically you drop one of these three things out on each of the flashcards and quiz yourself as to what would be replaced. If you had this starting material and this product and a question mark here, then you could help yourself memorize that PBr3 does this. Now, the mechanism is shown in your text, and I will walk you through it really quickly, but I'm not going to hold you responsible for all of the details. You do need to know that this reaction proceeds via SN2 and gives you inversion of configuration. What I'll show you now may help you remember what happens, but again, we're not going to put too much emphasis on all the mechanistic nuances. So one of the things that helps explain what goes on in this reaction is something that you wouldn't know unless you looked it up in a table, but that is that phosphorus-oxygen bonds are pretty strong. So actually there's a pretty good driving force to do a substitution reaction on the phosphorus with the oxygen attacking the phosphorus and the bromo leaving group leaving. It's almost like doing SN2 on the phosphorus. We've never done that before. It's okay if you wouldn't have been able to predict that this would happen. And the explanation for this is just that oxygen-phosphorus bonds are pretty strong. So at this stage, what you've got is the oxygen of the alcohol is now positively charged. Again, it might not be immediately clear, but what I have circled, and I'm going to now color in green, we're going to say is a good leaving group. You wouldn't know that without actually having it leave and then thinking about the pKa of its conjugate acid. We could look up that information, but for our purposes, it will be enough just to say, okay, that's a good leaving group. It looks a little bit like the water leaving group that we had last time. Apparently, it's not a good enough leaving group to just leave on its own. Instead, it waits around to leave before Br- does the attacking. You might ask, why is that the case? Why does the leaving group of water just pop off when we use acid, but for PBr3, when we have that strange looking leaving group, why does it wait for the nucleophile to attack? I don't know. Other than the people invented this reaction, found that it works. So bromo attacks, the leaving group leaves, and that gives you your desired product. Okay? Again, I'm not going to hold you responsible for this part of the mechanism or remembering that the oxygen-phosphorus bond is strong, but you do need to know that bromo displaces the leaving group to give you SN2 products. Questions about that? Yeah.
So it's SN2, but it's more like 2 steps.
It's SN2, but it's 2 steps, yes, in the sense that first I make this a good leaving group, and once it's a good leaving group, then this is the SN2 step. Yeah, good. All right, so we're going to have an alternative as well for making alkyl chlorides out of alcohols. The reagents here are going to be a little bit different, and there are going to be some questions as to why it's this way. The reagent is SOCl2, which if you draw the Lewis structure of that, it's a sulfur doubly bonded to an oxygen with 2 chloros attached. This reagent has a name as well other than SOCl2, but most people that I've ever interacted with in the class don't bother learning that, but if you want to sound posh, you can talk about thionyl chloride. But I don't know that it's necessarily worth that. Pyridine is a base. It looks like this. It's like benzene, only one of the CH's has been replaced by a nitrogen. Pyridine's a decent, moderate strength base. And you're going to have a question as to why for option 2 we needed a base, whereas for option 1 we didn't. And the answer to that question is, I don't know. When you're inventing new reactions, you often try to get them as high yielding and as fast as possible. And so often you try adding a bunch of things to the reaction to see if it helps. Presumably along the way they found that this reaction works better when you add pyridine as a base instead of just SOCl2 on its own. All right, so we can take the same starting alcohol. We'll react it with SOCl2 and pyridine, the base. And the effect of this is to replace the OH group with Cl. Again, the key step is an SN2 step that proceeds with inversion of configuration. As before, the effect of these reagents is going to be first to turn the OH into a good leaving group, and second to have chloride displace that leaving group in an SN2 step. I will show you this mechanism, but again, I will tell you that I'm not going to hold you responsible for it. We'll try to talk through a couple of the nuances, but some of the details you're just going to, you may just need to memorize some of the details. So let's see. As with the PBr3 reagent, the first step is that the oxygen is going to attack the sulfur. The sulfur has chloride leaving groups on it, so that sounds pretty reasonable. And the sulfur-oxygen bond is actually pretty strong. So, by analogy to what we did before, the first step with SOCl2 is, again, alcohol attacks sulfur and chloro leaves. And we've got an intermediate that's going to look like this. So far, it looks pretty similar to what we saw above with PBr3. I'm going to now show you what your text says happens. Some of you at this stage are saying, hey, why doesn't chloride come in and just attack and give you... Okay, how long were you going to let me do that? We good? Sorry. Some of you are asking at this stage, why does chloride not come in and kick this leaving group off? And the answer is, I don't know. But the fact that the base is present and is necessary for the reaction to proceed in decent yield and reaction rate suggests that what happens at this stage is the base removes that proton on the positively charged oxygen. Based on, what we've done before in our chapter on acids and bases, you should be pretty comfortable looking at that proton on the positively charged oxygen and saying, okay, yeah, that's probably pretty acidic. So that would generate this intermediate. And then, of course, you'd have the conjugate acid of your base. And what I'm saying is if we compared pKa's of this proton and this conjugate acid of our base, it would be very clear that this is a perfectly reasonable acid-base step. Okay? Why that's necessary, I don't know. And that's why I'm not holding you responsible for this mechanism. What happens next then is the chloride, and watch what this has in common with the PBr3 reaction. The thing that eventually replaces your alcohol is embedded in the reagent. That bromide is the thing that replaces your alcohol, and it was embedded in the PBr3. Similarly, the thing that's ultimately going to replace our alcohol was this chloride, which is embedded in the SOCl2 reagent. All right? So it's at this stage that chloride does the SN2 step. That sounds like a dance, the SN2 step. Now, what is shown here is an excellent leaving group. And the reason it's an excellent leaving group is that it can fall apart into even more stable things while it's leaving. So again, this is consistent with what your text shows. I would not expect you to predict that this would happen. But the fact that it does provides some insight into why this is a good reaction. As the oxygen is leaving, the electrons from the oxygen can kick down to form a new strong sulfur-oxygen pi bond, and then chloro can leave. That gives you this SN2 product, but the leaving groups that left are Cl-, which you should recognize as a good leaving group, and then neutral SO2, sulfur dioxide, which is a gas and bubbles off. Now we've talked before about delta G's for reactions depending on enthalpy, which is an issue of are the bonds you form stronger than the bonds that you break? And then we've talked about entropy, which is does the system have more freedom and more disorder after the reaction or before? Anytime you make a gas during a reaction, that gas has much more degrees of freedom than do molecules in solution. So entropy increases dramatically. This probably provides some of the driving force for this reaction to go and to be efficient. Probably removal of the proton is necessary so that the leaving group can collapse to form a gas. So that's probably some of what's going on. That being said, the mechanistic details aren't that important here. I've talked through it so that you can sort of understand what's going on, and hopefully that will help you remember this reaction. But what you need to be able to do for this reaction is, given a starting material and the reagent, predict the product, or given a product and a starting material, provide the reagent, or given a product and a reagent, identify what the starting material was. And you'll need to be able to master those stereochemical issues. Okay, questions? Yeah?
For protein, should we also memorize the gas formed as well as the chloride?
No. So for products, do you need to memorize that these two are formed? No. If you want to remember it for your personal edification, but no. Yeah. Okay. So those are two options that do SN2 reactions, and we don't get a mixture of stereoisomers as products, which is awesome. I'm now going to introduce a third reaction, and then I'll give you an example that contrasts how these first two reactions work versus the third. Okay. So let's see. So the final set of reagents is para-toluene sulfonyl chloride. That sounds horrible. We'll abbreviate it as TSCl. And again, we're going to be using pyridine as a base. All right, what is para-toluene sulfonyl chloride? Toluene is benzene, but with a methyl group. Para refers to the fact that what I'm going to add next is 1, 2, 3, 4 at the 4 position relative to my methyl group, exactly opposite on the benzene ring. You'll learn more about what para and other words like that mean in 352. The sulfonyl chloride has two oxygens, both doubly bonded to sulfur, and then a chloro leaving group. You can buy this reagent, it's a solid, you can buy it and store it on the shelf for long periods of time, so it's pretty useful. And if you take this reagent, I will just abbreviate it as TSCl and pyridine. The effect is to convert the oxygen into a good leaving group, but to pause after the oxygen has become a good leaving group. And this intermediate, well, it's not an intermediate now, this is actually a stable product. I want you to contrast that with what we did above, say in the SOCl2 reaction. We likewise converted the oxygen into a good leaving group, but this was not a stable product we could isolate. Instead, chloro came in from the backside to replace that good leaving group in a substitution reaction. For reasons that are not explained in your text, toluene sulfonyl chloride will convert the OH into a good leaving group, but we pause here at this stable product, and the chloro doesn't come in and attack. Why? Don't know. But this is chemistry that works beautifully. This is now, instead of a toluene sulfonyl chloride, this is a para-toluene sulfonate ester. But instead of calling it a para-toluene sulfonate ester, we abbreviate that and call it a tosylate. So there's the TO for ta. S, sil, and 8. Okay, and often chemists will not actually draw out all of that. They will simply abbreviate that as OTS. Okay, so that's going to have stereochemical consequences. I will again draw the mechanism for you, though I'm not going to hold you responsible for the details of the mechanism. It would be maybe difficult for you with this unfamiliar reagent to predict that what I'm going to show you would happen. If you, again, master this reaction at the level of starting material, reagent, and products, that should be sufficient. Mechanistically, what happens is the oxygen attacks the sulfur, and then the chloride leaves. You make a new strong oxygen-sulfur bond, and I will show you the intermediate that forms as a result. Again, you're going to have a positively charged oxygen with a proton on it. We have added pyridine to this reaction. It's one of our reagents, and so it seems reasonable for the basic nitrogen to remove the proton on that positively charged oxygen. We haven't looked up any pKa's, but if we did, we would see that the pKa of that proton on the positively charged oxygen is such that it's totally reasonable for the pyridine to remove that proton. And there we stay. Now, it's true that the chloro group left, right, in this step. And so it's true that sort of hovering around here in the background, we have a Cl- that could be a nucleophile. And it's not immediately apparent from the mechanism why Cl- comes in and attacks here, but doesn't come in and attack there. And I really don't have an answer for you as to why that is. So this may be a detail that you just have to memorize. All right, and I'm realizing that my sideways benzene rings look kind of like distressed robots of some kind, so, yeah. All right, so why do we care about this? Let me show you a couple of ways that you can use these reactions to generate different stereochemical outcomes. So, suppose my starting material is this alcohol. It's chiral, and it's got two stereocenters. One of them is going to be involved in the reaction, and the other isn't. So I'm going to now do a two-step reaction series, PBr3, and then in the second step, I'm going to add sodium azide. Sodium is just the counter ion. Azide is the nucleophile. So after step one, step one is going to convert that OH into the bromide. What should the stereochemistry be at this carbon for the Br group? Dash or wedge? Dash, because we get inversion of configuration, right? Then in step two, we add our, now we're back to chapter 7 and 8 chemistry. We've got a secondary alkyl halide. We've got something that is a good nucleophile but a poor base. So we expect only SN2. So now the azide nucleophile attacks from the backside in SN2 fashion, and in my product I should have N3 up. Okay, two tandem SN2 reactions, right? First we replace the OH with the bromide, then we replace the bromide with the azide. Two successive tandem inversion steps leads to the nucleophile having the same relative configuration as the alcohol to begin with. Now, what if instead of that, I want you to contrast that with what would happen if instead we used paratoluene sulfonyl chloride to turn the OH into a good leaving group. So here, instead of using PBr3 in the first step, I'm going to use paratoluene sulfonyl chloride and pyridine. And then in the second step, I'm going to again use sodium azide. Sodium is simply the counter ion. azide is the good nucleophile, that's a good base. Notice, based on what we just talked about, that if we use para-toluene sulfonyl chloride, that should make the tosylate without having chloride come back in from the backside and do a displacement. So we've made this stable product, the tosylate, and we haven't changed the stereochemistry on where that oxygen was. But we now need to talk about the characteristics of this tosylate group. And I'm going to tell you that this tosylate group is a good leaving group. Why is that? Oh, there we go. Good leaving group. It may not appear to be so. So what I'm going to do is draw for you the SN2 reaction. I'll show the tosylate group leaving, and then I'll show what it leaves as, and it will become much clearer why it's a good leaving group. Before we do that, just note that if the azide does SN2 chemistry on the tosylate, that you end up with a product in which the azide is down instead of up. In other words, just by switching the reagents, we can get a different stereoisomer, which is kind of cool to have reaction-based control of the stereochemical outcome of a series of reactions. Along the way, let me show you what leaves. TSO minus is equal to this. Good leaving groups are conjugate bases of strong acids. So we would want to draw the conjugate acid of TSO minus, which would be para-toluene sulfonic acid, or in other words, this reagent, or rather this molecule. Now, just, look at this. What does that look like? What have you seen before that looks kind of like that? If you squint and sort of stop paying attention to the carbon portions of the molecule, what does the rest of it look like? Kind of looks like sulfuric acid? Yeah. Remember that from Gen Chem H2SO4? This is like an organic soluble version of sulfuric acid, and it's actually quite acidic. This proton has a pKa of -11. So it's a super strong acid, which means the TSO minus is a really great leaving group. Now again, I know somebody out there is thinking, if it's such a great leaving group, then how come it doesn't leave? You've got the chloride nucleophile there. How come it doesn't do the SN2 reaction? And again, I'm sorry, I got nothing. But the idea is then, if you accept that the tosylate is a good leaving group, we now have 3 strategies for turning the OH into a good leaving group, 2 of which result in immediate inversion of configuration. That's PBr3 and SOCl2. But the tosylate is able to do this and stop before you get inversion of configuration. And so then we can go on in a subsequent step to use the tosylate in the exact same way as we would use any other molecule with a good leaving group on it. We can do substitution and elimination reactions with these tosylates, and things work just fine. All right, yes?
So can the chlorine, like if you introduce chlorine in the second step, it still won't be bromine, or it still won't send off?
If you introduce chlorine in the second step, will it? I don't know, actually, it's a good question. We can pretend like that works.
Okay.
Then you have to deal with the issue of, well, why didn't it do it to begin with? And I don't know.
Mm-hmm.
Okay, other questions? Yeah?
would this happen in a tertiary carbon?
Right, so would it happen with tertiary carbons? No, because you can't do SN2 at tertiary carbons. So sure, you'd use these reactions would be useful for secondary alcohols and primary alcohols. The tosylate actually you could easily do with the tertiary carbon, because remember with the tosylate you don't do the SN2 step immediately. It would just be a question of what could you do with the tertiary tosylate. You could do elimination chemistry, I suppose, but yeah. All right, what else? So what we've done so far has been doing substitution chemistry with alcohols. We focused on reagents like HCl and HBr that give us SN1 products. And we focused on reagents like PBr3 or SOCl2 that give us SN2 products. And we just introduced this weird reagent, para-toluene sulfonyl chloride, that can convert the OH into a good leaving group without it actually leaving or doing subsequent substitution chemistry. To round out the story, we want to talk about elimination reactions of alcohols. And as we have done with substitution reactions with alcohols, there are going to be two basic stories. One is going to be acid promoted elimination reactions of alcohols, and those are going to have carbocation intermediates and rearrangement possibilities. So we're going to do that, and then we're going to introduce a third, we're going to introduce another new reagent that can do elimination chemistry without a carbocation intermediate. So that's our theme. You got standard make a carbocation ways of dealing with alcohols, but beware of rearrangements, and then you have a reagent that's going to avoid that problem. So elimination reactions of alcohols are called dehydration reactions because you lose the OH and you lose a beta proton, which is the same thing as losing water, so dehydration. So let me show you a couple of different ways you can do this under acid catalyzed conditions. Here is a secondary alcohol, and we're going to use H2SO4 as a reagent. This is your text uses this, and this is a fairly simple way to introduce the reaction. Let me just say that sulfuric acid is such a strong acid that nobody really does a lot of chemistry with it. It can do a lot of undesired side reactions on a lot of other functional groups in organic molecules. So what I'm about to show you is not the most useful reaction, but it's instructive. So some of you are panicking having seen H2SO4. I know this because I have a son who's in Chemistry 106, and the phrase polyatomic ions strikes fear into his heart, as does the phrase polyprotic acids. And anyway, you're probably wondering, do we have to memorize the structure of H2SO4? Well, okay, fine. It's not that hard, but no. Because most of the time in mechanisms, when you want to show an acid doing its thing, you can abbreviate it as HA, and organic chemists are going to know exactly what you mean. So when you use sulfuric acid, the first step is to protonate the alcohol to turn it into a good leaving group. So that should be familiar based on what we did before last time. That turns the alcohol into water, which is a good leaving group. As before, we expect the water to leave. Oops, that's not what I wanted. We expect the water to leave to give us a secondary carbocation. There's the proton that's on that carbon that was implied but not shown. At this stage, with a secondary carbocation adjacent to a tertiary carbon, I'm worried about rearrangement. So if I do a 1,2 hydride shift, that would allow, and all I need to do that is a single arrow. This hydrogen on the tertiary carbon leans over, takes its electrons, and attaches to the carbon that was the secondary carbon. That's going to convert my less stable secondary carbocation into a more stable tertiary carbocation. This would be an equilibrium process. It could go forwards and backwards, though you would think that it would be better to have a more stable tertiary carbocation. I want you to show the products that would come from both of these. So having established that those are both carbocationic intermediates, I'm going to redraw the secondary one so that we can draw elimination products that would come from that one. Here we're looking for protons that are beta to the positive charge. From this point on, it's just standard E1 type chemistry. So blue beta proton and orange beta proton. If we remove, I will show the mechanism for removal of one of those protons. What does the removing? Well, you got to understand that sulfuric acid comes in aqueous solution. So you have H2SO4 and water. What does the removing could either be the conjugate base of H2SO4 or it could be water. Either of those is okay. I think your text shows the conjugate base of H2SO4. There's probably a lot more water than there is of that, so I tend to like showing water doing it. It doesn't really matter. So I'm going to show you just that arrow to give us the blue elimination product, which would look like this. Of course, if we removed the orange beta proton, we should get this product. I deliberately chose my example so that there would be no stereochemical issues. Do you see how with both the blue and the orange products, there's no cis-trans issues to worry about at all? Yay. If there were, you'd have to draw both cis and trans products. Now let's look at the tertiary carbocation. We'll call this pink beta proton, and then we need another color. I like to avoid red-green colorblind issues, but I think I'm out of colors, so there's green. I'm very sorry. If we remove the pink beta proton, we would get, which is the same as the orange one, right? So actually, well, no. Get a sneeze. Shoo, sorry. Ooh. Excuse me. I have a brother-in-law that does sneeze impressions. I didn't know this was a thing. The triple line there represents that these two are the same product, so don't misunderstand me there. Yeah, he listens to people sneeze, and then he tries to imitate their sneezes. But it's tough to sneeze on cue, so to do this, he pulls his nose hairs out, and that generates sneezing. It's really kind of gross, but... Okay, so those are the three products that you would get. Notice that if you did this reaction and you saw this green product, that is evidence for a carbocationic intermediate, because the only way you could get that green product is if there was a rearrangement. Okay? So you can use sulfuric acid to do this. You have an alternative reagent. You could just use para-toluene sulfonic acid if you were in a situation where sulfuric acid was causing you trouble. This is that conjugate acid of the tosylate leaving group. We abbreviate this as TSOH, and it is basically an example of an organic soluble sulfuric acid. Okay, so you could use this reagent to do this same E1 type chemistry. Any questions about that mechanism? I mean, you could sort of ask, why don't we get substitution products here? Why do we just get elimination products? And the answer is, I don't really know. One other asterisk that you may want to put in your notes is that this reaction is actually in equilibrium, because when we go to chapter 10, we are going to take alkene starting materials, and under acidic conditions, we're going to go back towards the alcohol. That sounds horrible at this point. Notice that the leaving group, the thing that left, was water. And if indeed this is an equilibrium process and you want to drive it forward, one of the things you can do is remove water from the equilibrium to use Le Chatelier's principle to push this reaction forward. There's actually some really easy and straightforward experimental techniques you can use to remove water from a reaction mixture. And that perhaps is another reason why you'd want to use organic solvent and paratoluene sulfonic acid if you really wanted to drive things toward that dehydration product. Okay, the last thing we're going to do, not ever, just today, is show you that if you take this same starting material but use a new reagent called POCl3, a lot of phosphorus today, a lot of chlorides, and then again we're going to use pyridine as a base, you will get, this reaction proceeds through an E2 mechanism. You will get products from removal of the orange beta proton and the blue beta proton, but importantly, you will not get any of the rearranged products. And the reason you don't is the same reason that we didn't get two enantiomers with using PBr3 or SOCl2 is that this reagent is going to convert the OH into a good leaving group, and then the elimination is going to happen, and that leaving group isn't going to leave on its own. As before, you're going to have the same sorts of questions here as to why doesn't it leave? Why does the chloro not come in and do substitution chemistry? And as before, I'm not going to have any answers for you. You're just going to have to memorize that POCl3 and pyridine lead to elimination products with E2 reaction mechanism. I will draw that mechanism for you, but not today, so that you can see it. But again, you will need to memorize what this reagent does. Okay, been a long week. Have a good weekend. We'll see you Monday.